The spectrum comes up on the screen, and something is wrong with it. Not broken, wrong. The break in the light sits at a wavelength that should be empty. Push it through the math, and you get a galaxy shining 280 million years after the Big Bang. And it is not a smudge. It is bright. It is compact. It looks finished. That was supposed to be the good news. Webb working better than promised, breaking its own record again. Here is what nobody put in the headline. That galaxy is one of dozens that arrived too early. In the same 4 years, the measured expansion rate of the universe stopped agreeing with itself, and the last easy excuse for that disagreement was eliminated. 3 cracks, 1 model, 1 telescope that nobody can ever go up and repair. The record is not the story. The pattern is. The object has a name. MOEM Z14. It sits at a redshift of 1444. And when the confirmation paper cleared peer review and appeared in the Open Journal of Astrophysics, the write-ups all landed on the same word. Farthest. Most distant. Earliest. A new frontier. All of that is true. None of it is the interesting part. Before I go further, tell me where you are right now. Genuinely, I want to know, because there is something useful in it. Whatever time it says on your wall, whatever city you are in, the light I am describing left its source before there was an Earth to have a wall or a city or a clock. It crossed a universe that spent 13 billion years rearranging itself while that beam was in transit, and it ended its journey inside a machine parked 1 million miles behind our planet's shadow. Drop a comment. Say where you're watching from. I'll come back to why that matters. Now, the part that should bother you. Webb has broken this record 4 times, not once. 4 times, in roughly 3 years of operations, each time by a margin that surprised the people who set the previous mark. And every time it happens, the same sentence appears in the coverage. Scientists were surprised to find galaxies this mature this early. Read that again, slowly. Not this far away, not this faint, this mature. Distance is not the anomaly. Webb was built to see far. That was the entire point of the 18 gold-coated beryllium segments, and the tennis court sunshield, and the decade of delays, and the $10 billion. Seeing deep into the early universe is the mission succeeding exactly as designed. Maturity is the anomaly. Because a galaxy that is bright and compact and chemically enriched is not a beginning, it is a middle. It is the result of a long industrial process that takes gas, cools it, collapses it, ignites it into stars, lets those stars live and die, and seed the surrounding cloud with heavier elements, and then does it again. That takes time, a lot of time. And Webb keeps finding the finished product in a window where our best model says the factory should still be under construction. So here is my thesis, stated plainly, because I am not going to hide it and make you wait 20 minutes for it. Webb did not find light older than the universe. That is not possible, and I will explain exactly why in a moment. What Webb found is light that arrived too early for our model of how matter assembles. And in the same handful of years, the same telescope helped harden a second problem about how fast the universe is expanding, while a completely separate instrument in Arizona produced a third result suggesting that dark energy may not be constant at all. 3 independent cracks. In one model. Inside 4 years. The comfortable framing is that this is an exciting puzzle. Science working. Anomalies are how progress happens. You have heard that framing, and I want to be careful here because it is not wrong. It is just incomplete in a way that I think matters. Because here is what the comfortable framing leaves out. Every one of those cracks was surfaced by, or depends on, a single observatory. That observatory sits 1.5 million kilometers from Earth, in a place no human being can reach. It carries a finite amount of propellant. It has already taken permanent, uncorrectable damage from a rock the size of a grain of dust. Its operating budget has been slated for reductions of roughly 20%, and the technology program meant to build its successor had its funding request cut by more than 80%. Let that sit for a second. We have opened the deepest window on cosmic history that our species has ever had. That window is showing us that our model of cosmic history may be wrong in at least 3 places. And the window has a service life, a fuel gauge, and a budget line that somebody has already started shrinking. I am not telling you the sky's falling. I am telling you that the story everybody repeated, Webb found the oldest light ever, is the softened version. The unsoftened version is stranger and considerably less comfortable, and you can assemble the whole thing from published papers and public budget documents. Nothing here requires a secret. But we have to start with the headline itself, because the phrase that went around the world, light older than time itself, is not an exaggeration. It is impossible. And that impossibility is not a gotcha about sloppy science journalism. It is the loose thread. Pull it, and the entire comfortable version starts coming apart in your hands. Nothing can be older than time. Not in this model, not in any version of it. The reason is definitional, and it is worth being precise about, because the precision is where the real problem lives. In standard cosmology, the Big Bang is not an explosion that happened inside time at some particular moment. It is the boundary of time. It is the point past which the equations stop returning answers. Asking what came before is not a hard question with a hidden answer. It is a question the framework does not accept as well-formed, in roughly the way that asking what is north of the North Pole is not a hard question about geography. So a photon older than the universe is not an extraordinary discovery. It is a contradiction in terms. Any headline containing that phrase has already told you it did not come from the paper. And the papers did not say it. What the teams reported in the flat, careful register that these things get written in is that certain galaxies have been spectroscopically confirmed at redshifts above 14, placing them under 300 million years after the Big Bang, and that their brightness and inferred masses sit uncomfortably above what standard galaxy formation models predicted for that epoch. That is the actual finding. It is less cinematic and considerably more disturbing. Here is how the distortion happens, and I don't think it requires anyone to be acting in bad faith. A press release says, earliest galaxy yet observed. An aggregator turns that into oldest light ever seen. A second aggregator, working from the first, reaches for a superlative that has not been used yet and lands on older than time itself. By the fourth iteration, nobody in the chain has read the paper. Each step was a small stretch. The accumulation is a claim that is not merely wrong, but backwards. And backwards is the key word, because look at what got lost in translation. The public came away thinking the surprise was age. Webb saw further back than expected. Impressive, but conceptually boring. A bigger telescope sees further. That is what bigger telescopes do. The actual surprise was maturity. And that is not a story about the telescope's power. That is a story about the universe's schedule not matching our model of it. Now let me clarify what I'm not saying, because this is exactly the point in a video like this where the voice usually goes off a cliff, and I would rather stay credible than get clicks. I am not saying the Big Bang is wrong. The evidence for a hot, dense early universe is overwhelming and comes from directions that have nothing to do with each other. The microwave background, the relative abundances of hydrogen, helium, and lithium, the expansion itself. You do not overturn that with a handful of bright galaxies. I am not saying scientists lied or covered anything up. Every number in this video came from a public paper, a public press release, or a public budget document. Nobody hid this. Some of it was simply phrased in language calibrated not to alarm. I am not saying Webb malfunctioned. Webb is performing above specification in almost every measurable way. The instrument is not the problem. The instrument is the messenger. What I am saying is narrower, and I think harder to dismiss. The reassuring version of this story only works if you ignore the specific thing that surprised the researchers. And when you stop ignoring it, the shape of the problem changes completely. Because a mature galaxy at 280 million years is not just an early galaxy, it is a claim about rates, about how fast gravity can pull gas together, about how fast stars can form, burn, and die, about how fast a black hole can grow. Those rates are not free parameters we get to adjust to taste. They are constrained by physics we think we understand well, and by observations of the nearby universe that took a century to accumulate. So when the observation and the model disagree, you have exactly three options. Option 1. The observation is wrong. The redshift is misidentified. The mass estimate is inflated. This has happened, and I will show you a specific case where it happened badly. Option 2. The model needs adjusting. Star formation was more efficient early on. The first stars were more massive. Dust behaved differently, all plausible, all being actively worked on. Option 3. Something more fundamental is off, and these galaxies are the visible edge of it. Most working astronomers would put their money somewhere between 1 and 2, and they would be reasonable to do so. I am not going to pretend the field has concluded otherwise, but here is the thing that keeps pulling my attention back. Options 1 and 2 both assume we can trust the ruler, and that assumption is doing an enormous amount of quiet work. Because we did not measure that galaxy's age. Nobody measured it. We measured how stretched its light was, and then we converted that stretch into a number of years using a model. The same model the galaxy is supposedly contradicting. Think about what that means for a second. The evidence and the framework being tested are not independent. They are entangled. The number that makes the galaxy look impossible was produced by the very thing the galaxy is calling into question. That is not a scandal. Every science does something like this. But it is a structural weakness, and it means the question we should be asking is not how did that galaxy get there so fast? The question is, how do we actually date a photon? Because once you understand that process properly, the anomaly stops being an isolated curiosity about one bright object. It becomes something that could, in principle, be wrong everywhere at once. Start with what the light actually does on the way here. A photon leaves a star in a young galaxy. It carries a specific wavelength, set by the physics of the atom that emitted it. That physics does not change. Hydrogen behaves the same way in the first billion years as it does in a lab in Munich today. This is the anchor the entire enterprise rests on. Then the photon travels. And while it travels, space itself expands. Not the photon moving through a growing container, the container growing underneath it, stretching the wave along with everything else. By the time it arrives, the crests are further apart than when it left. Blue light becomes red light. Red light becomes infrared. Push it far enough, and visible light lands entirely outside the range your eyes can process. Which is precisely why Webb is an infrared telescope, and precisely why it has to be kept cold enough that its own warmth does not drown out the signal. Redshift is the ratio of that stretch. That is all it is. It is not a distance, and it is not an age. It is a measurement of how much bigger the universe got while the light was in transit. So how do you know which stretch you are looking at? You need a landmark in the spectrum, a feature you can recognize no matter how far it has slid. The best one is a wall of hydrogen. Neutral hydrogen in intergalactic space absorbs light below a certain wavelength almost completely. Above that threshold, light passes. Below it, it is eaten. The result is a cliff in the spectrum. On one side, signal. On the other, almost nothing. That edge is called the Lyman break, and it is the single most important landmark in the deep universe because it is sharp, it is universal, and it travels with the light. Find the cliff. Measure how far it has moved from where it should be. That ratio is your redshift. Now the numbers, and I want to walk you down them properly rather than just leaving them sitting there. JWST 14.0 came in at a redshift of 1432. Take that ratio and run it through the standard expansion history, and you get an emission time of roughly 290 million years after the Big Bang. Compare that to the age of the universe, which is about 13.8 billion years. 290 million into 13.8 billion is close to 2%. Now, make it something you can hold. Compress all of cosmic history into a single calendar year. The Big Bang is midnight on January the 1st. Every star you have ever seen with your naked eye, every element in your body, every human being who has ever lived, all of it happens later in that year. That galaxy is shining in the first week of January, before the second Monday, and it is not a wisp. It is bright, compact, and already carrying elements heavier than hydrogen and helium, which means it has already built stars, burned them, and killed them at least once. Now the human consequence, which is where I think the number finally lands. Every heavy atom in your body was manufactured inside a star. The calcium in your teeth, the iron carrying oxygen through your blood right now as you watch this. That manufacturing has a schedule, and the schedule is the thing we are dating. So when the schedule looks wrong at the beginning, it is not an abstract dispute about a distant smudge. It is a dispute about the timeline that produced you. Here is the part I find genuinely difficult to shake. That galaxy's light arrived at Webb's mirror not as a beam, but as individual photons, trickling in, one at a time at a rate you could almost count. Which is why the observations take hours, and why the mirror has to sit at around 40 Kelvin. Because at ordinary temperatures, the telescope's own infrared glow would flood the detector completely. The instrument has to be colder than the thing it is looking for. So picture it honestly. A gold-coated surface, 6.5 meters across, held near absolute zero in permanent shadow, catching a handful of particles that have been in flight since before the sun existed. Then a computer converts that handful into a number of years. And that conversion is the weak point. Because here is what the process actually gives you, stripped of the press release. Webb measures a wavelength. It measures the position of a cliff. It measures brightness. Those are measurements. They are real, repeatable, and about as solid as observational astronomy gets. An age is not one of them. To turn a redshift into a number of years, you need the full expansion history of the universe. You need to know how much matter it contains, how much dark matter, how much dark energy, and whether dark energy has stayed constant across all that time. You feed those assumptions in, integrate, and out comes a date. Change the assumptions and the date changes, not the observation, the date. So when somebody says a galaxy existed 290 million years after the Big Bang, what they are reporting, precisely, is this. Given the standard model of cosmology, this observed stretch corresponds to that moment. That is an inference. A good one, built on decades of cross-checked work. But an inference. And now hold that next to the anomaly. We are using the standard model to calculate an age, then using that age to declare that the standard model has a problem. That is not circular exactly. The observations do constrain things independently. But it does mean the ruler and the object being measured share a common failure mode. If the model is off in the right way, the anomaly could partly be an artifact of our own measuring stick. Which raises a question I think most coverage skips entirely. If the ruler is built out of the thing it is measuring, how would we know if the ruler was bending? Here is a story that should be told far more often than it is. In 1929, Edwin Hubble published the measurement that established the universe is expanding. It is one of the genuine turning points in the history of science, and the number he attached to it was about 500 kilometers per second per megaparsec. The modern value is somewhere around 70. He was wrong by a factor of 7. Not slightly off. Not within the error bars. Off by an amount that, taken at face value, made the universe younger than the rocks on Earth. And the reason was not incompetence. Hubble was using the best calibration available, and the best calibration available happened to be built on a misunderstanding about the kinds of pulsating stars he was using as distance markers. The observations were fine. The interpretation of the observations was catastrophically off, and it stayed off for decades before anybody sorted it out. Hold that next to what we just established. Every age Webb produces is an inference built on a chain of calibrations. And the chain has broken before, in living memory, in a way that made the whole picture temporarily absurd. It broke again in the 1990s. Astronomers measuring the ages of globular clusters, dense, ancient balls of stars orbiting our galaxy, kept getting numbers in the region of 16 to 18 billion years. Meanwhile, the expansion rate implied a universe of perhaps 12. stars older than the cosmos that contained them. That is not a subtle tension. That is a flat contradiction, and it sat in the literature for years. It got resolved, eventually, and it got resolved in a way I think is worth paying close attention to. Not because somebody found an error in the star ages, because dark energy was discovered, the expansion history was revised, and the universe turned out to be older than the previous model said. Read that again. The contradiction was resolved by the model changing, not by the data being wrong. That is precedent. That is a case where a mismatch between what we saw and what we predicted was pointing at missing physics the entire time, and the community spent years assuming it was a measurement problem. Now, the counterexample, because I promised you I would not stack the deck. Early in Webb's operations, a candidate called Sears 93316 appeared in the photometric data at an apparent redshift of around 16.7. That would have been extraordinary, well beyond anything else on the board. It got attention, it got headlines, then somebody got a spectrum. The real redshift was 4.9, not 16, under 5. A galaxy from a much later, much more ordinary era, wearing a disguise made of dust and unusual emission lines that happened to mimic the color signature of an extremely distant object. The photometric estimate, the quick method, based on brightness through different filters, had been fooled completely. This is the honest counterweight, and I want to give it full force. Some fraction of the impossible early galaxy problem has already evaporated under closer inspection, and more of it may yet. The scientists doing this work know that better than anybody, which is exactly why they chase spectra rather than announcing from photometry. But notice what that episode actually demonstrates. It demonstrates that the quick method can be off by a factor of 3. It demonstrates that our confidence in a distance can collapse the moment better data arrives. And it demonstrates that the field has a live, unresolved problem with distinguishing very far away from dusty and closer than it looks. So which direction does that cut? Both. That is the uncomfortable answer. It cuts against the alarming interpretation, because some anomalies are artifacts. It also cuts against the reassuring interpretation, because if the method can be wrong by that much in one direction, the ruler is softer than the confidence intervals suggest in general. And here is the thing that stops this from being a comfortable stalemate. The objects that survive spectroscopic confirmation are still there. MOEM Z14 has a spectrum. JWST Z14-0 has a spectrum. These are not photometric guesses that will quietly deflate. They have been through the filter that killed Sears 93316, and they came out the other side. And there are enough of them now that surveys can start measuring how common bright early galaxies are, rather than arguing about individual cases. That statistical shift matters more than any single record. One weird object is a curiosity. You can explain a curiosity with a lucky alignment, a rare burst, a chance viewing angle. A whole population is a rate problem. A rate problem is a physics problem. So let me put the argument where it actually stands, without inflating it. The ruler is model dependent. That is a genuine structural weakness, and it means every age quoted in this field carries a hidden asterisk. History says the chain of calibration has snapped before, both because the data was misread and because the physics was incomplete. Some of the current anomaly is probably measurement, some of it is probably interpretation, and some fraction of it has now survived every check we know how to apply. What I want you to take from this is not that the numbers are meaningless. They are not. They are the best numbers anybody has ever produced about the deep past, and the people producing them are rigorous about their own uncertainty in a way most professions never manage. What I want you to take is that the phrase we know, the universe is 13.8 billion years old, is doing something subtler than it sounds. It means, given a model that fits an enormous body of evidence, this is the implied age. And that model is currently under pressure from at least 3 directions at once. Which brings us to the part where the intuitive response fails. Because most people, hearing that galaxies form 20 or 50 million years earlier than expected, will file that under close enough. 20 million years against 13.8 billion is a rounding error. Surely the model just needs a nudge. That instinct is completely reasonable. It is also completely wrong, and understanding why is the moment this stops being an academic dispute. Here is the assumption I need to break. You probably think of building a galaxy the way you think of filling a bath. Turn the tap higher, the bath fills faster. Need it done sooner. More water pressure. The task is the same task, just accelerated. Structure formation does not work like that. Not even slightly. What actually has to happen, in order, is this. Gas has to collect under gravity. To collapse, that gas has to shed heat, because a hot cloud has too much internal pressure to fall inward. Shedding heat requires something to radiate it away, and in the very early universe your options are severely limited, because the only elements available are hydrogen, helium, and a trace of lithium. There is no carbon, no oxygen, no dust. The efficient coolants that let gas clouds collapse in the modern universe do not exist yet, because they have not been manufactured yet. So the first stars form slowly, and they form enormous, because inefficient cooling produces massive clumps. Those stars live fast and die violently. Their deaths scatter the first heavier elements into the surrounding gas. Now cooling gets easier. Now the next generation can form faster and smaller and more like the stars we recognize. Every step in that chain depends on the previous step finishing. You cannot parallelize it. You cannot turn the tap higher. The universe has to build its own tools before it can use them, and each round of tool building costs the lifetime of a generation of stars. That is why the timeline is not a dial. It is a dependency chain. Now compress it. Take a process that requires several sequential generations and force it into 280 million years. And remember what that window contains. Expansion is still rapid. Densities are dropping. The gas is still almost pure hydrogen and helium. You are asking the least efficient possible version of the process to run at the highest speed it has ever run. That is a categorical change, not a quantitative one. It is the difference between a factory running overtime and a factory that has to build its own machine tools while filling the order. Now let me show you where this gets genuinely hard, because galaxies are not the worst of it. Black holes are. Webb, along with X-ray observations, has turned up supermassive black holes in the early universe at masses reaching into the tens of millions of solar masses, and in some cases around 100 million, at epochs where standard formation theory struggles badly to produce them. Here is why that is worse than the galaxy problem. Black holes grow by accretion, and accretion has a speed limit. As material falls in, it heats and radiates. That radiation pushes outward on the material still falling. Past a certain luminosity, the push balances the pull, and the inflow chokes itself off. That threshold has a name and a number, and it means a black hole's growth is roughly exponential, with a fixed doubling time of tens of millions of years. Run the arithmetic backwards. Start with a black hole formed from a collapsing massive star, a light seed, maybe 100 solar masses. Let it eat continuously at the maximum sustainable rate, with no interruptions, no gaps, no periods where the gas supply fails. Ask how long it takes to reach 100 million solar masses. You need close to 1 billion years. We are seeing them at a few hundred million. The timeline does not close. And it does not close by a factor that no amount of nudging fixes. So what are the options? One is heavy seeds. Skip the star entirely. Have a giant gas cloud collapse directly into a black hole of tens of thousands of solar masses, giving you a running start. Simulations of this scenario now reproduce a good deal of what Webb sees, and several groups have argued the observations favor it. Another is that the speed limit gets exceeded, not violated. The limit assumes a tidy, spherical, steady flow, and reality is messier. Under the right geometry, matter can be funneled in faster than the simple calculation allows. Recent work models these objects as black holes caught in violent, short-lived feeding episodes running above the standard rate. Then there is the population that has caused the most argument of all, the little red dots. They turned up almost immediately in Webb's data, and nobody knew what they were. Extremely compact, distinctly red, present in far greater numbers than anyone predicted. They appear less than 1 billion years after the Big Bang and have mostly vanished by 2 billion, which is bizarre on its own. A whole class of object that switches on and off in cosmic history. They also break the diagnostics. They show broad emission lines, which normally means gas whipping around a black hole at enormous speed. But they emit almost no X-rays and almost no radio, which is exactly what a feeding black hole is supposed to produce. The explanations have been arriving fast, and they disagree with each other. One analysis of the highest quality spectra argues the lines are broadened by electron scattering in a dense ionized cocoon rather than by orbital motion, which would cut the inferred black hole masses by around 2 orders of magnitude. Another set of simulations argues they are direct collapse black holes, the long-sought heavy seeds, finally caught in the act. A third proposes super Eddington bursts. Notice what that means. 4 years in, with the best infrared observatory ever built pointed directly at them, the community cannot agree on the mass of these objects to within a factor of 100. I want to be fair about this, because it can be read 2 ways. It genuinely is normal for a new class of object to be contested for years. Nobody should expect resolution this fast, and the pace of competing explanations is a sign of a healthy field working hard, not a broken one. But hold it against the scaling problem we just walked through. Every proposed fix buys the timeline at a price. Heavy seeds require a formation channel we have never observed. Super Eddington growth requires sustained conditions we have never measured. Reduced masses solve the growth problem and immediately create a new one, because now you have to explain why these things are so absurdly luminous. You do not get the time for free. Every solution moves the debt somewhere else, and that is still the abstract version, because so far this has all been gas, gravity, and accretion rates, numbers on a screen, which is where I think most explanations of this stop, and where I think they lose the thread entirely. This schedule is not abstract. You are standing on the output of it. There are somewhere around 1 kilogram of calcium in your skeleton, not manufactured on Earth. Earth has no mechanism for making calcium. That calcium was fused inside a star, and then that star died, either blew off its outer layers or detonated, and scattered the result into a gas cloud, which eventually collapsed into a disk, which eventually became a rocky planet, which eventually became you. The iron in your blood right now, carrying oxygen to your brain while you watch this. Same story, forged in stellar cores or in the violence of a stellar death. The oxygen it is carrying, same. The carbon in every protein in your body, same. The only elements you contain that came directly from the Big Bang are hydrogen and a little helium. Everything else is secondhand. Salvage. Now here is the connection I want to make, because I think it is the part that gets left out of every version of this story. The timeline we have been arguing about is the manufacturing schedule for the atoms you are made of. When we say the first stars formed at some particular epoch, we are saying when the factory switched on. When we say early galaxies were already chemically enriched, we are saying the first production run had already finished and the second was underway. When Webb finds that enrichment happening earlier and faster than the model allows, it is not making a claim about distant smudges. It is making a claim about the supply chain that produced your bones. Sit with that for a second, because I think most people have never been given the chance to. You are not observing this history from outside it. You are the late-stage product of it. Every argument about cooling efficiency in primordial gas is, several billion years downstream, an argument about how the calcium got made. Your body is a physical record of a process whose opening chapter is currently being rewritten, and here is the part that genuinely unsettles me. If the early timeline is wrong, if enrichment ran significantly faster than the standard picture allows, then the assumption underneath a great deal of what we think about our own arrival is unstable too. When did rocky planets first become possible? That depends on when heavy elements became abundant. When did chemistry complex enough for life become available anywhere? Same dependency. Every one of those estimates inherits the early timeline's uncertainty, silently, without an asterisk. We do not usually notice that inheritance because the numbers get quoted with such confidence. Now let me bring in the other set of human beings in this story, because there is a second body count here that never gets mentioned. The people doing the work. Webb's observing time is allocated in cycles, roughly a year each. Researchers write proposals. A committee reviews them. Time gets awarded. In Cycle 4, astronomers submitted 2,377 proposals from 39 countries. 274 were selected. Around 8,500 hours of observing time were awarded, the most in the telescope's history to that point. 2,377 down to 274. That is roughly 9 rejections for every acceptance. Now translate that. Behind a great many of those rejected proposals is a person who has spent years preparing for a question they cannot answer any other way, not a mild preference, a career, a PhD student whose thesis needs those hours, a postdoc on a 3-year contract who needs a result before the contract ends. There is no alternative instrument. If you need to see a galaxy at redshift 14, there is exactly one machine in existence that can do it, and you have a 1 in 9 shot at a slice of it. Think about what that concentration means. An entire generation of researchers has organized its working life around a single object in space. Their questions, their funding, their timelines, their students' futures, all downstream of one telescope's operating schedule. And it goes further than career risk, because there is a stranger kind of dependence buried in this. The people who built Webb spent, in many cases, their entire working lives on it. The design work began in the 1990s. Engineers joined the program in their 20s and retired before it launched. There are people who worked on that sunshield for 2 decades and watched the launch as pensioners. The instrument that is currently unsettling cosmology was assembled by a generation that mostly did not get to use it. That is not a sad footnote. It is the actual shape of how this kind of knowledge gets made. One group builds the apparatus and hands it forward. The next group asks the questions, which means the answers we get are always constrained by decisions made by people who could not know what would be found. And the decision that shaped everything here was where to put it. And here is where I have to say the uncomfortable thing. We have been talking about Webb as though it were an institution, a fixed feature, something that will simply be there, the way a national library is there. It is not an institution. It is a machine. And machines have a service life. It carries a finite quantity of propellant. It has already sustained permanent damage that cannot be repaired. It sits in a location no human being can reach, has ever reached, or is currently planning to reach. Every question we have raised in this video, the early galaxies, the impossible black holes, the whole argument about whether the model holds, depends on continuing to collect data from that one object. So the next question is not about cosmology at all. It is about hardware, and it is considerably more fragile than most people assume. The Moon is about 384,000 kilometers away. Webb sits at roughly 1.5 million, 4 times further, and not in orbit around Earth, which matters more than the raw distance does. It is parked at a gravitational balance point called L2 on the night side of our planet, in a position that lets it keep the Earth, the Moon, and the Sun all behind the same shield permanently. That geometry is the entire reason the telescope works. Break the geometry and you break the instrument. It also means nobody is coming. Compare that to Hubble, and I want to do this comparison carefully because it is the single clearest illustration of what we have traded away. Hubble launched in 1990 with a flawed primary mirror. The polishing was off by a fraction of the width of a human hair, and the images came back blurred. It was, at the time, a national embarrassment. The most expensive telescope ever built could not focus. In 1993, a space shuttle crew flew up and fixed it. They installed corrective optics, essentially a pair of spectacles for the telescope, over 5 spacewalks. Hubble went from punchline to the most productive observatory in history. It was serviced 4 more times after that. New instruments, new gyroscopes, new batteries. Hubble's operational life has been extended repeatedly by human hands. That entire model of operation is unavailable to Webb. Not difficult, not expensive, unavailable. There is no crewed vehicle, current or planned, capable of reaching L2, performing a repair and returning. Webb has a docking ring on it, a small gesture towards some hypothetical future robotic refueling mission. And that is the extent of the plan. Hope. Now, what has already gone wrong? In May 2022, before science operations had even properly begun, a micrometeoroid struck one of the 18 primary mirror segments, segment C3. The impact was larger than anything the engineering models had anticipated in that time frame, and it left a deformation that could not be fully corrected. Some of the effect was compensated by adjusting the segment's alignment. Some of it was not. It is simply part of the instrument now. One grain of dust. Permanent. And that is not a design failure. Everyone knew this would happen. Space is full of debris moving at enormous speed. And over 20 years, a mirror sitting in the open will accumulate hits. It is the expected cost of doing business. But think about what expected means when there is no repair option. Every strike is cumulative. Every strike is forever. The mirror Webb has today is the best mirror it will ever have. From here, the only direction is degradation, at whatever rate the debris environment dictates, with no floor beneath it other than the end of the mission. Then there is fuel. Webb needs propellant to hold station at L2 and to point where it is told. The tank was filled once. The launch was accurate enough that less fuel was consumed getting there than planned, which brought years of extra life and was rightly celebrated. Current estimates put the propellant lifetime at something over 20 years. 20 years sounds like a long time. Let me translate it. The telescope took roughly a quarter of a century to build and cost around $10 billion. It launched at the end of 2021. So the useful scientific life of the instrument is roughly comparable to the time it took to construct, and a meaningful fraction of it has already been spent. Now put that against the 9-to-1 oversubscription. There is more good science requested than there is telescope, by a factor of 9, in a machine with a fuel gauge that only goes one way. And here is the compounding problem, the one that turns a hardware constraint into something worse. The anomalies we have been discussing are not the kind you settle with one good night. Confirming a redshift 14 galaxy takes hours of integration. Building the statistical sample needed to say whether bright early galaxies are common or rare takes hundreds of hours across many fields. Resolving what the little red dots actually are will require deeper spectra of fainter objects, which is to say more time, on the only instrument that can do it. The questions Webb raised require Webb to answer. That is the structural trap. This is not a case where the discovery is done and the analysis can proceed on the ground for decades. The discovery generated a new observational program, and that program is bounded by the same finite, unrepairable, unrefuelable machine that generated it. So let me put the shape of this plainly. We built one instrument capable of seeing this era. We put it somewhere unreachable. It found evidence that our model of cosmic history may be incomplete in ways we did not anticipate. Answering the questions it raised requires substantially more of its time. And it is running on a tank that was filled once, with a mirror that only degrades, at a location where nothing can be fixed. I am not saying this was the wrong design. The L2 orbit is why Webb can do what it does. The thermal environment there is what makes the sensitivity possible. You could not have built this telescope in low Earth orbit and had it work. The trade was deliberate and, on the physics, correct. But a trade is a trade. We bought capability with irreplaceability. And you would think, given all of that, that the response to a finite window producing model-threatening results would be to fund it harder while it lasts. That is not what happened. Watch the language for a moment, because I think it is doing more work than people notice. When measurements of the universe's expansion rate refused to agree with each other, the field settled on a word for it. Not a discrepancy, not a failure, a tension. When Webb found galaxies that the model struggled to produce, the standard phrasing was that researchers were surprised, or that the results were challenging for existing theory. When the little red dots defied every diagnostic, they became a puzzle. Tension, surprise, challenge, puzzle. Every one of those words has something in common. They all describe a situation that is interesting rather than serious. They frame the anomaly as an opportunity, and critically, none of them contain any suggestion that the framework might be in trouble. Now, I want to be extremely careful here, because this is where a video like this can turn into something I have no interest in making. This is not a conspiracy. Nobody sat in a room and chose these words to mislead you. There is a much more ordinary explanation, and once you see it, it is more troubling than a conspiracy would be, because you cannot fix it by exposing anybody. Scientific institutions are structurally required to be cautious. If you announce that the standard model of cosmology is broken and you turn out to be wrong, your credibility is finished. If you describe it as a tension requiring further study, you are correct regardless of the outcome. The incentive gradient points one direction only. Understatement is free. Overstatement is career-ending. Layer onto that the funding environment. Research budgets are political. They are approved by people who are not astronomers, in competition with everything else a government pays for. In that environment, we found an exciting puzzle at the frontier of knowledge: is a fundable sentence. Our foundational model may have serious problems, and we are not sure how deep they go, is a sentence that invites the question of why anyone should keep paying. So the language stays warm. Not because anyone is lying. The papers themselves are precise, and the uncertainties are stated plainly for anyone who reads them. But the layer that reaches the public gets sanded smooth, and the smoothing is systematic in one direction. And then this happened. Webb's operations are managed by the Space Telescope Science Institute. In early 2025, the head of the Webb Mission Office told an audience at an American Astronomical Society meeting that the institute had been asked to consider a cut of roughly 20% to the mission's operational budget, and that the effects would reach across essentially every part of the mission. The federal budget request for the 2026 fiscal year proposed reducing Webb's funding from $187 million to $140 million. Estimates discussed at the time put the potential reduction in operations somewhere in the range of 25 to 35%. Part of the underlying problem is not political at all. The operating costs were set back around 2011, when the telescope was fighting for its life against cancellation, and they were set optimistically, low enough to survive the political moment. Add 15 years of inflation to an optimistic number, and the shortfall arrives on schedule, regardless of who is in office. And then the piece that I think is the most revealing of all. The same budget request cut the Technology Maturation Program for the Habitable Worlds Observatory, the proposed successor, the next flagship, the instrument meant to carry this work forward, from $17.5 million to $3.3 million. That is not a delay. Cutting a technology maturation program by more than 80% is how you push a mission from the 2040s into the indefinite. So line it up. The telescope is finding results that put pressure on the standard model of cosmology. It is the only instrument capable of following those results up. It has a hard lifetime limit measured in years. Its operating budget is being reduced by roughly a fifth to a third. And the funding for the technology that would eventually replace it has been cut by more than 80%. Now, the fairness clause, because I promised. Budgets are proposals until they are enacted, and proposals get modified. Congress has restored science funding before. The specific numbers in any given request are not destiny, and anyone telling you Webb is being switched off tomorrow is not being straight with you. I am also not saying the people making these decisions are stupid or malicious. Every agency runs a portfolio, and every line in it has a constituency that considers it essential. Somebody has to choose. What I am saying is this: when an instrument produces results that suggest your framework has a problem, and that instrument has a finite life, the rational response is to maximize what you extract before the window closes. We are doing something closer to the opposite. And the soft vocabulary, the tensions and the puzzles and the surprises, is part of why almost nobody has noticed, because at no point has anyone been told anything urgent enough to object to. There is one more layer to this, and it is the one nobody controls. The public calibrates its concern to the temperature of the announcement. That is not stupidity, it is a completely sensible heuristic. If the experts sound relaxed, You assume the situation is relaxed because you have a life to run and you cannot personally audit every field of science. But the heuristic breaks when the experts are institutionally required to sound relaxed, and it breaks in a particular direction. Astronomy is one of the few sciences the public consumes purely as spectacle. Beautiful images, records broken, cosmic wonder. Nobody's insurance premium depends on the value of the Hubble constant. So there is no external pressure group demanding a straight answer, no industry lobbying for clarity, no constituency that gets angry when the framing goes soft. The field is free to understate, and the audience is primed to accept it. And soft vocabulary is exactly how you would fail to notice that three separate things had gone wrong at once. Put them side by side. That is all I want to do here. The first crack is the one we have spent most of this on. Mature galaxies and overweight black holes appearing in a window, our model of structure formation struggles to accommodate, with each proposed fix creating a new bill somewhere else. The second crack is the expansion rate. There are two ways to measure how fast the universe is expanding, and they are almost completely independent of one another. The first works outward from nearby objects. Measure distances to pulsating stars whose brightness you can calibrate. Use those to calibrate exploding stars visible much further away, and read off the rate. This is the distance ladder. It has been refined for a century, and it gives a value around 73 kilometers per second per megaparsec. A 2026 analysis combining data across multiple telescopes reported 73.5 with an uncertainty under 1. The second works forward from the beginning. Take the microwave background, the oldest light in existence, released when the universe was around 380,000 years old. Measure the pattern of ripples frozen into it, feed that into the standard model, and calculate what the expansion rate should be today. That gives 67.4, with an uncertainty of half a unit. 73.5, 67.4. The error bars do not touch. They do not come close to touching. The gap is roughly 5 standard deviations, which in physics is the threshold where you stop calling something a fluctuation. For years, the reasonable assumption was that somebody had a systematic error. Crowding in the star fields, perhaps, nearby stars blending together and corrupting the brightness measurements. Dust, calibration drift. Webb was, in part, sent up to check. 4 times Hubble's resolution in the near-infrared. It re-observed the same stars in the same galaxies. The crowding explanation did not survive. The local measurement held. And I have to give you the honest counterweight, because it exists. A separate team led by Wendy Friedman has argued for years that different distance markers, red giant stars, carbon stars, give values closer to 70, consistent with the standard model. That work is serious, and it is not going away. There is a real, live disagreement between careful groups about which markers to trust. But notice the shape of even the optimistic reading. The best case is that our distance calibrations disagree with each other in ways we cannot yet resolve, using the finest instrument ever built. That is not reassurance. That is a different problem wearing reassurance as a costume. The third crack is dark energy, and it is the newest. Dark energy is the thing making cosmic expansion accelerate. It accounts for most of the energy content of the universe, and the standard model treats it as a constant, the same everywhere, at every epoch, never changing. That assumption is baked into every age calculation in this video. The dark energy spectroscopic instrument has been mapping millions of galaxies to test it, and its second data release reported a preference for dark energy that changes over time rather than staying constant. Depending on which datasets you combine, the reported significance ranged up to about 4.2 sigma. And that result is contested, genuinely contested. Multiple groups have published analyses arguing that the preference is driven by tensions between the datasets being combined rather than by new physics, and that the significance depends heavily on which supernova catalog you use. This is not settled, and I will not pretend it is. So take the deflationary view of all three. Say the early galaxies are partly a modeling artifact. Say the expansion disagreement is an unresolved calibration problem. Say the dark energy hint dissolves under better data. Even then, look at what you are left with. 3 independent probes of the same framework, run with the best instruments ever constructed, and all 3 return results that do not fit cleanly. The optimistic reading is not that everything is fine. The optimistic reading is that we have 3 simultaneous measurement problems we cannot currently solve. And I want to give you the historical comparison because this pattern has a track record. For decades, Mercury's orbit was slightly off, not dramatically. A tiny excess in the precession of its closest approach to the Sun, well under 1/100th of a degree per century. Astronomers assumed an undiscovered planet. They named it in advance. They searched for it. There was no planet. The discrepancy was gravity itself being incompletely described, and it took general relativity to explain it. Around the same time, the way hot objects radiate energy refused to match theory at short wavelengths. It was a technical embarrassment in a corner of the field. Resolving it produced quantum mechanics. Small anomalies are usually nothing. But the ones that were something looked exactly like this beforehand. Persistent, resistant to easy explanation, and initially filed as calibration problems. I'm not telling you the standard model is finished. I do not know that, and neither does anybody else, and anyone who claims otherwise is selling you something. I am telling you that we are in the configuration where that has historically happened. Multiple probes disagreeing, explanations proliferating, vocabulary staying calm. And this time there is a difference that the Mercury astronomers did not have to deal with. They could keep watching Mercury indefinitely. So here is the verdict. The light is not older than time. It never was. That phrase came from an aggregation chain, not a paper, and the truth underneath it is stranger than the exaggeration. The truth is that the universe appears to have assembled itself faster than our model says it could. That the 2 independent methods for measuring its expansion have refused to agree for over a decade, and the easiest explanation has now been ruled out with the best instrument we possess. That the constant we assumed dark energy to be may not be constant, and that all 3 of these results are being pursued with an observatory that has a fuel gauge, a degrading mirror, no repair option, a shrinking operating budget, and a successor program that has been cut past the point of momentum. The comforting thing people say at this juncture is that science is self-correcting. Anomalies get resolved. The system works. I want to take that seriously because it is mostly true. And then I want to point at the part of it that is not. Science is not self-correcting in the abstract. It is self-correcting through instruments. The 1990s contradiction between star ages and the age of the universe was not resolved by thinking harder. It was resolved by supernova surveys that found dark energy. Hubble's factor of 7 error was not resolved by reflection. It was resolved by better telescopes and a corrected calibration. Correction requires apparatus. Apparatus requires funding. Funding requires that somebody with a budget believes the question is urgent. And the vocabulary we have built around these results, tension, puzzle, surprise, challenge, is precisely calibrated to communicate that nothing is urgent. That is the mechanism, not suppression, not a cover-up. A slow mismatch between how serious the results are and how serious they are permitted to sound, running at exactly the moment when the instrument capable of settling them is on a clock. Let me be clear about what I am not saying, one last time, because it matters more here than anywhere else in this video. I am not saying we should stop, the opposite. Everything in this story is an argument for going harder while the window is open. I am not saying the researchers are hiding anything. Every fact here came from a public paper or a public budget line. They wrote it all down. Most of it just never got read by anybody outside the field. I'm not saying the Big Bang is wrong, or that cosmology is a house of cards, or that you should distrust scientists. Distrust is the cheap conclusion, and it is the wrong one. The people producing these numbers are the ones who found the problems in the first place. Nobody caught cosmology out. Cosmology caught itself. What I am saying is narrower. The physical situation is harder than the public framing, and the window for resolving it is not open indefinitely. Now let me give you the genuine hope, because it exists, and I would not have earned the right to your attention if I left it out. The Nancy Grace Roman Space Telescope is designed to survey enormous swathes of sky in the infrared, and it could launch as soon as late 2026. It will not replace Webb, different instrument, different job, but it will find the candidates that Webb can then confirm, which is precisely the bottleneck right now. The DESI survey has been extended through 2028, which means the dark energy question gets substantially more data rather than staying frozen at a contested 4 sigma. Euclid is already returning results, and Webb itself keeps breaking its own records, which means the frontier is still moving. None of that is nothing. Some of these questions may well be answered within the decade. But go back to where we started. A spectrum on a screen, a break in the light sitting where nothing should be. A galaxy that looks finished 280 million years after the beginning of everything. When that image went around the world, it was framed as a triumph. Look how far we can see. I think it is better understood as a notice, because that light spent 13.5 billion years in transit. It crossed a universe that expanded by a factor of 15 underneath it. It arrived at a 6.5-meter mirror held near absolute zero, 1.5 million kilometers from the nearest human being. And it landed there during a window of a couple of decades in which our species happened to have built something capable of catching it. That window was not inevitable. It required a quarter-century of work, $10 billion, and a run of political luck that nearly failed several times. Webb came close to cancellation more than once. There is a version of the last 30 years, not far from this one, where the program died in committee and none of these questions were ever asked, and nobody would have known what we were missing, because you cannot miss a result you never obtained. That is the part I keep returning to. Not that the model might be wrong. Models are always provisionally wrong. That is what makes them useful. What gets me is that our ability to find out is not a permanent feature of the world. It is a machine, built by people who are now mostly retired, running on a tank that was filled once, and it closes. The light is not older than time. Our understanding is younger than we admitted, a great deal younger, in at least 3 places we can currently point at. We finally built the instrument that could tell us how much we had wrong, and we are reading the answer on a timer.